about images. Today we will be mainly talking about images. We will be talking about the beginning of image processing. It's called low-level vision. Then we'll talk about edges, how you find edges, how you group regions in an image. In other words, if you have a satellite image, how do you find out which area is grass, which area is forest? So that is texture segmentation. Segmentation means how do you separate an image into parts? So we will talk about segmentation, coloring. Blob coloring was also covered in computer graphics. It's part of segmentation. It's a technique for segmentation. We will talk about contours. Contours is more than edges. It connects the edges. So you can, very often when you see some shape, like you're familiar with the heart shape, you recognize what it is based on the shape, or an apple. Okay? So these are called contours. So we study contours for recognition. We talk about the general Huff technique. I've done quite a bit of research in this area. So at each of these, I will try to introduce my own research work and other people's research work, Dr. Bandit, for example, and so on, so that you can see how it can be made practical. We will talk about optics, these energy minimization techniques. For those of you who have taken advanced mathematics for PhD students, you have seen these techniques before. We will spend just about the same number of hours on it, about 3 or 4 lectures on energy minimizing, or it's called optimization. Now, optimization is how do you find the maximum or the minimum of something, and that's a very, very important, very crucial knowledge for solving computer vision. The reason is, in computer vision applications, you lose a lot of information from projection. You see, when the images, the world is 3-dimensional, but the image is 2-dimensional. So you lose a lot of information just because of that, for example. But there's a lot more information lost than that. So you need to be able to find that lost dimension. And optimization means to find the best solution. Optimization is some sort of way of doing the best solution. And usually we have to do nonlinear optimization. So we will be studying optimization techniques as a basic, like in form of mathematics. We'll be looking at it in its pure sense. And then we will look at applications of that to stereo matching, to motion, to all kinds of things. Now, what do I mean by that? We will be talking about depth from 2 images. That is called stereo vision. We'll be talking about depth from texture. We'll be talking about depth from motion. When things move, how do you find distance? We will be talking about recognition from motion. We will be talking about object recognition. That's like the last topic. Structure from motion. How do you get shape? When you see an object moving, how do you get shape? For example, when you drive a car, you will notice that things that are near you will move fast, but the building that's far away moves very slowly. So this kind of information can provide you is information on distance. One interesting research area, for example, is if you put a camera instead of at the red light at an intersection where you have traffic coming, sometimes at night there's no traffic, but still the signal will go red because there's no sensor to see if there's any traffic. Now, one very standard sensor is to dig in the ground and put these weight sensors on the floor of of the road, on the surface of the road, and basically it's a weight sensor. When a car comes, then they know that there's a car a car has stopped at the red light, so maybe it will turn green. Otherwise, it's always red, because it's a very small street, for example. So, for example, you have a road like this, and this is a small sawyer, you know. You can make it like that. And the red, the light here is always red, and the light here is always green. So it's green so that cars can, on the main road, can keep going. But when there's a car that comes over here, the sensor knows, okay, there's a car, maybe we will turn this red and let this car go. Usually in Thailand, we use a traffic police for this because, you know, it's not worth it to put a red light and all that logic to it. But I think an interesting topic would be, this is a research topic, would be if we could get a camera to look and see if there's any car on the road. Now, a car should not be a bicycle, because bicycles can go on their own. So the camera should be able to distinguish between a car, a truck, a bicycle, a motorcycle. So it gets more and more interesting, and it can maybe tell what kind of car is there, and then based on that, so it's a RoboCop, you know. RoboCop. Cop means police, right? You've heard of RoboCop, but this will be a Robo-Traffic Cop. It's an interesting problem, I think, to have one computer and one camera just look, and the computer will process the image and control the traffic light in that way. It's possible. A good research topic for undergrad or master's level, I think. So this is an example of image understanding as well. So we will learn about these techniques. We will also learn about camera calibration. How do you know, when a camera really looks at something, there are models about where the points in the 3D image falls on where 3D points falls on the 2D image. And we will look at calibration to see how those models really fit, how the data really fits the model, and if it doesn't, how to modify the data so that it fits. So that's called calibration. And I'll talk more about it. I'm just trying to give you a general idea right now, a general idea about the topics in computer vision that we will be covering. So we will cover just about every topic that is in this book. Actually, we'll cover pretty much all the topics in a first-year computer vision class. We will. I try to teach from the bottom up, so I usually don't assume that you know have any basic mathematics or any basic background, really. Even computer graphics. It helps to have a computer graphics background, but if you don't have it, I think you can still, I don't think there'll be any problems. So it's not a problem if you don't have any of that background. But of course, when it comes to maths, you should know how to invert a matrix. You should know how to multiply a matrix, solve equations. You should know how to differentiate equations a little bit. Not much of that either. So very, very simple elementary calculus you should know. But other than that, this class doesn't really have much requirement in terms of background. Okay? So it's an introductory course. You can come in and be relaxed that you're not expected to have or to know any serious background, except what's expected from somebody who's gone through 3 years of an engineering program should at least know, in terms of mathematics at least. Engineering or computer science program should know. Okay? So I will entertain some questions right now. You know what I'm going to do? I am going to turn my phone on.